Hello everyone, welcome back. So in this video we are going to learn about system output and stability. Okay, system output and stability of the system based on pole's location. Okay, so based on pole's location we are going to now see how the system output will be and how can we find the stability of the system based on different pole's location. Okay, if you are first time to my channel, please consider subscribing. So when the case 1, we will take different cases. Okay, so different cases for different location of poles. So if the poles lies in the left half of S-plane, okay, so the poles are real poles. If the poles are real poles, then and if it lies in the left half of S-plane, then so in this case, suppose so this is a real pole like this. This is sigma and this is minus sigma, this is j omega and this is minus j omega. So I'm taking this pole as -2. You can take any value. Okay, so the transfer function is 1 by s plus 2. So impulse response, inverse Laplace transform of this becomes impulse response. So C of t is e power minus 2t into u of t. Okay, so e power minus 2t into e of t. So it is an exponentially decaying signal. So if the pole lies in the left half of S-plane, which are real in nature, then the output is exponentially, okay, so exponentially decaying signal. The output is exponentially decaying signal and the system is stable. Okay, so this is case 1. Now we'll take another case 2. If the poles are complex conjugate with real part in the left half of S-plane. Okay, so if the poles are complex conjugate with real part in the left half of S-plane, that means the poles will be like this, like some value you can take here, like -2, and this is plus j1 and this is minus j1, and there are poles like this. Okay, so now the poles are complex conjugate and the real part of the poles lies in the left half of S-plane. So poles are complex conjugate with real part in the left half of S-plane. So for such type of value, so transfer function now becomes 1 by, so what does it become? 1 by s plus 2 plus j1 is one pole, s plus 2 minus j1 is one pole. Okay, so that it will be, so if you make it equal to 0, s is equal to -2 minus j1. So this is the pole, -2 minus j1. S is equal to -2 plus j1. -2 plus j1 is this one. Okay, so the combination of these two. So the combination here is -2 plus j1, -2 minus j1. Okay, so that is how the complex conjugate poles exist. So combining that, what you will get? 1 by s plus 2 whole square. This is, if you take this total s plus 2 as a and b, and this is again a and this is b, so a plus b into a minus b, so a square minus b square, so s plus 2 whole square minus b square, so minus of j square 1 square is plus 1. Okay, plus 1 square. Okay, so if you find the transfer function, so impulse response C of t will now becomes my e power minus 2t into sine t, e power minus 2t into sine t. Okay, so if you draw e power minus 2t into sine t, so this is your t and this is C of t, so it is exponentially decaying, because due to this term it is exponentially decaying. Okay, and sine t, it is not only exponential decaying, but it is multiplied by sinusoidal signal, so the output will be like this. Okay, so the output will be exponentially decaying sinusoidal signal or sinusoidal oscillations. Okay, what is the other name for exponential decaying sinusoidal oscillations? Is damped oscillations. Okay, so we are going to call it as damped oscillations, that is decreasing in amplitude, so that is called as damped. Okay, so the system is said to be stable still because the poles lies in the left half of S-plane only. Since the pole lies in the left half of S-plane, the system is stable and the output is exponentially decaying sinusoidal oscillations when the poles are complex conjugate with real part in the left half of S-plane. Okay, so these are the two cases when the poles are in the left half of S-plane. Okay, so next we will see the case 3. So if the poles lie in right half of S-plane. Okay, so right half of S-plane. So if the pole lies in the right half of S-plane like this, so I will take it as 2. So sigma here and minus sigma, this is j omega and minus j omega. Okay, so in the right half of S-plane and the poles are real in nature. Okay, so if the poles are real in nature, then transfer function is given by 1 by s minus 2, so that s is equal to 2 is the pole. Okay, so its corresponding impulse response C of t is e power 2t into u of t. Okay, so e power 2t into e of t. So if you draw this on this, so if you draw this C of t versus t, so e power 2t is this like this. It is an, so output is exponentially increasing signal. Okay, so output is exponentially increasing. Okay, so as t tends to infinity, then C of t also e power 2t, so it is e power infinity. Since t is equal to infinity, so it is also equal to infinity, so C of t is equal to infinity. That is, it is unbounded. Okay, so it is unbounded. So when input is bounded and when the output is unbounded, then such type of system is said to be unstable system. Okay, so it is said to be unstable system. Okay, this is how we can find the instability. So since the location of poles, this is one method of defining the stability, and this is the other method of defining or finding the stability also. Okay, so if the output is unbounded, then it is an unstable system. Next, case 4, if poles are complex conjugate, the poles are complex conjugate with real part in the right half of S-plane. Okay, right half of S-plane. That means the poles are like this. Okay, so this is sigma and this is minus sigma, this is j omega and this is minus j omega. So the poles are like this. They are complex conjugate with real part in the right half of S-plane. So 2 I will take, this is J1 and this is minus J1. Okay, so then transfer function will be 1 by S minus 2 plus J1 and S minus 2 minus J1, so that the poles will be S is equal to 2 minus J1. So 2 minus J1 is this pole, so 2 minus J1, and the other pole is S is equal to 2 plus J1, so 2 plus J1 pole is this. Okay, so transfer function is 1 by S minus 2 whole square plus 1 square plus 1 square. Okay, so if you find the impulse response, C of t is e power 2t into sine t. So it is also now the product of an exponential term multiplied by a sinusoidal term, but the exponential here in this case is exponentially increasing signal. Okay, in case 2 we have seen the same, but it is an but there it is an exponential decreasing signal, but here it is exponentially increasing signal. So if you draw this, if you draw the C of t, so it is an exponentially increasing signal. Okay, and it is multiplied by sine t. So the output is exponentially increasing sinusoidal signal like this. Okay, so output is exponentially increasing sinusoidal signal. Okay, so exponentially increasing sinusoidal signal. So as t tends to infinity, e power 2 power 2t sine t is also tending to infinity, because this term becomes infinity. Infinity to into anything is also equal to infinity. So it is also an unbounded output. It is also an unbounded output. Even if you see here also, it is unbounded. It is increasing exponentially and does not decrease anywhere. Okay, it is an unbounded signal. So unbounded output, sorry. So the system is unstable system. Okay, unstable system, because poles lies in the right half of S plane. Okay, so this is the difference between the real poles and real poles and complex conjugate poles, which lies in the right half of S plane. Okay, so in the previous 4 cases, the first 2 cases are the poles lies in the left half of S plane, the second 2 cases are poles lies in the right half of S plane, and now we'll see 2 more cases for the poles lying on the imaginary axis. So case 5 is non-repeated poles. Okay, so non-repeated poles on imaginary axis. Okay, so non-repeated poles on imaginary axis. So if poles are non-repeated and which lies on imaginary axis, suppose J1, J2 here and minus J1, complex conjugate only, so minus J2. Okay, so they are non-repeated here. So non-repeated poles on the imaginary axis, then the system is marginally stable. System is marginally stable. Okay, so the system is marginally stable. So just remember this, non-repeated poles on the imaginary axis, system is said to be marginally stable. So we know that it is so transfer function will be of this form, s square plus 1 into s square plus something 4. Okay, s square plus 4, so that poles here is s is equal to plus or minus j1, s is equal to plus or minus j2 here. Okay, so if you take transfer function is equal to 1 by s square plus 1 minus 1 by s square plus 4, so you have to multiply with 1 by 3 of course. So C of t now becomes 1 by 3 into this is sine t minus sine 2t. Okay, So sin t minus sin 2t, still it is in terms of sinusoidal signal only, so the output will be a constant amplitude and frequency of oscillations. Okay, of course there will be some shift here, that is not a big problem, so we are discussing only about stability, so it will be this. Okay, so if there are non-repeated poles on imaginary axis, system is said to be marginally stable, and the output is constant amplitude and frequency of oscillations. Constant amplitude and frequency of oscillations, and the system is said to be marginally stable. Okay, when non-repeated poles are on imaginary axis. Case 6, the last case, when there are repeated poles on imaginary axis. When there are repeated poles on imaginary axis, then system is unstable. Okay, so if there are repeated poles on the imaginary axis, that is there are two poles at J1 and there are two poles at minus J1. If you take sigma here, and this is minus sigma, this is j omega, and this is minus j omega. So if such type of is there, then what will happen? So transfer function is equal to 1 by s square plus 1 whole square. So it becomes 1 by s square plus 1 whole square. Then c of t now becomes t into sin t. Okay, so t into sin t, when t is tending to infinity, then c of t is tending to infinity only, because this term becomes infinity. Okay, so infinity into anything is also equal to infinity, so it is an unbounded output. System is said to be unstable. So that is why system is unstable when repeated poles on imaginary axis exist. So if the poles are non-repeated, then system is marginally stable. Understand the difference? If the repeated poles are there on the imaginary axis, that is at J1 only we have two poles, and minus J1 you have again two poles. Not only two, it can be more also. Okay, so if the poles are repeated, then the system is unstable. Okay, so if you want to draw how will be the output, so it is multiplied by t, so it will be shifted here like this. So it is exponentially increasing. Okay, so it is multiplied by t. Okay, so t is a ramp signal, so it is of the form ramp here. Okay, a ramp signal will be like this, a straight line passing towards, and if it is shifted upward, so it will be this, like this. So it will be like this. Okay, so this is what the output will be. Okay, so t into sin t. Okay, this is a ramp signal and this is a sinusoidal signal. Okay, so this is about different types of location of poles and their corresponding outputs, and we can classify the stability of the systems. Okay.